All right, I'm gonna do a practice problem with you, and it's gonna be a torque equilibrium problem. It's gonna involve a ladder, and so I don't know if you've ever gone up a ladder before and gone, man, if this ladder slips, I am in trouble. But that's what this problem is going to be about. So you have a 5 kilogram, 3 meter ladder. It's resting against the wall. It's making a 20-degree angle with the wall. And you have to figure out the minimum coefficient of static friction, because we're hoping that it's not going to slip, so the ladder doesn't slip. Okay? And then we'll go from there. So let's draw a picture that represents the problem. Seems like a very good idea, don't you think? So here's the ground. Here's my wall. And let me draw the wall a little bit better. And then my ladder is going to be something like this, where this top angle is going to be 20 degrees. Okay? Hopefully, can you see that? I'll make it bigger over here when I draw my FBD, but that's what we're trying to do, and we're trying to find the coefficient of friction here. We're going to assume that there's very little friction here. So this we're going to assume is 0, and this is what we're trying to find. Okay? All right, so let's first draw our FBD. So we kind of drew a picture of what's happening, but I'm going to draw my FBD nice and big. So here's the wall, here's the ground, and we're going to draw a nice big FBD. And then remember, when we're drawing our FBDs in rotation with torque, you have to draw the forces where they are acting, and then you have to apply them that way. So, well, what forces are acting on my ladder? Well, I have the force of gravity acting on my ladder. Where is gravity going to act? Oh yeah, the center of mass of my ladder, which is going to be right here in the middle. Which way is it going to point? Oh yeah, it's going to point straight down. So there's going to be my FG. Okay? Then what other forces I might have acting on my ladder? Well, the wall is going to push this way on the ladder, and I am going to call that, yeah, it's a normal force, but this is also going to be a normal force. So just so that we know that they're different, I'm going to call that the force from the wall. Now, if there was friction here, if my ladder was going to slip, it would slip this way. So there would be an upward force of friction. We're saying that, hey, we don't have to worry about the friction with the wall. Down here, you're going to have a normal force going straight up. Straight up. Okay, Fn. And if you take a look, okay, hey, Fn and Fg better be the same size, because otherwise my ladder's not in equilibrium. So let's put a little dash mark to show, hey, those have to be the same size. Now, if I just had this, okay, if this was it, you can see my ladder is not going to be in equilibrium. How do I know that? Because, hey, these two forces cancel, but there's nothing canceling this force. So, yeah, that's not so great. So let's then say, well, there has to be something that's going to cancel that force. Well, which way is the force of friction going to act? It's going to act this way towards the wall. 1, because it has to cancel this force. 2, because it's going to prevent it from slipping. Okay, so let's draw that force in, and I want to draw it the appropriate size. I'm going to label it friction, and I'm going to say, hey, you know what? Those forces have to be the same size. Okay, so now, hey, I've drawn my FBD. Before I start messing this up with weird components and stuff like that, we're going to write our force equation, because we know how to write the force equation. It's easy. Well, I want to write an X force equation and a Y force equation, because I have horizontal forces and I have vertical forces. So let's do that. So, it's going to be this minus this. So I'm going to have force of the wall minus F of friction. Well, that has to be 0. That makes sense, right? And then if I do my vertical forces, I'm going to have Fn minus Fg. Hey, that equals 0, because, that makes sense, right? Well, if I was plugging stuff in now, I could say, well, all right, do I know how big Fn is? No, but I can find this. So I'm going to get Fn minus 5 times 9.8 equals 0. And then 5 times 9.8, I believe, is 49. Let's just verify. 5 times 9.8 Hey, it's 49. What do you know? It's going to be 49 newtons. So now I know how big Fn is. Oh, wait. Ff is mu times Fn. Oh, wait. So it's going to be the force of the wall minus mu s times Fn equals 0. And oh, shoot. I don't know how big that is. Guess what that means? Yep. That means we have to write our torque equation. Okay. So we're going to write our torque equation. So again, if we're smart about this, okay, when we're writing our torque equation, it's like, I could put, because remember, my ladder is in equilibrium. That means I can put my axis of rotation at any point I want. Why? Because it's not rotating, and hopefully it's going to stay not rotating. So then I'm going to pick a spot that's going to make the problem easier. Well, which spot could I put it where it's going to be like, hey, you don't have to worry about these in the torque. Well, if I put it here, that's going to make the force of the wall go away. If I put it here, that would make Fg go away. If I put it here, ooh, both of those go away. That seems easier. So guess what I'm going to do? I am going to put my axis of rotation. I'm going to put a nice big X here to show you my axis of rotation is going to be down there, and then I'm going to write my torque equation. But here's where you guys got to be careful. Remember, torque is this. If you look on your equation sheet, it's RF, and they put the little perpendicular here to remind you these have to be perpendicular to each other. Okay? Well, if I draw R in, okay, I'm going to draw it in here. Actually, I don't know, maybe I'll draw it over here so you can see. The R for G is going to go this way for the force of gravity, but the force of gravity points straight down. So I need to break it into its components. Hopefully you can see that. If you can't, zoom in. But this piece is the piece that's going to cause the torque. Why? Because that's the piece that's perpendicular to the lever arm. So if I break my force of gravity into its components, perpendicular and parallel, where this is going to be my 20-degree angle, hopefully we see that, okay, then I can now solve stuff. So if I write my equation, my net, so I'm going to write my net torque equation, or sometimes you'll see it written like this, where I'm adding all the torques up. Okay. If I do this, well, I'm going to have RG times FG perpendicular because that needs to be perpendicular to one another. And then I would be, now here's where you got to use your pencil. You're going to use your pencil. I'll use my meter stick here. I'm going to hold it like this. Everybody ready? I'm holding it here. Why am I holding it there? Because that's where the axis is. This force, whoop, whoop, whoop. Oh yeah. That would be clockwise. Everybody see that? Oh, this force, the perpendicular part of it, whoop, whoop, whoop. I know, good sound effects. That would be counterclockwise. So guess what? If this is clockwise and that's counterclockwise, I have to subtract them, which is good because if I had to add them, I would never get 0. But so this would be minus, okay, R for the wall times force from the wall perpendicular. And that has to equal 0, okay? Because it's in equilibrium. So, hey, in equilibrium, remember, if you're in equilibrium, net force must be equal 0, and net torque must be equal to 0. Super important, okay? That if net force, let me write it down. If you add all your torques up, you have to get 0. If you add all your forces up, you have to get 0, okay? So, in equilibrium. All right. So now let's plug our stuff in, and then we'll make sense out of this. So this would be, if it's a 3-meter ladder, this is going to be 1.5. Hopefully that makes sense. This is going to be this piece of it, which is, in this case, again, we got to draw our picture. Hopefully this makes sense. That would be the mg sine, because my 20 degrees is at the bottom. So it would be mg sine for that one. So it would be 5 times 9.8 times the sine of 20 minus the whole r to go up to there. That would be 3. And then I would have to break this into its components, where this would be the component because it needs to be perpendicular to that r. So there's my r, there's the component. So it would be 3. Hopefully we can see this angle there is 20 degrees, 20 degrees, okay? Which then means it would be force of the wall times, if that's 20, and that's this, then this would be adjacent to the 20, adjacent to the 20, so it'd be cosine, and then that equals 0. And I know, I'm an amazing singer. And then we can plug our stuff in, solve for FW. Let me do that. Need to be able to see. All right, 1.5 times 5 times 9.8 times sine of 20 is 25.14 minus 3 times cosine 20, 2.82 FW equals 0. So FW equals 25.14 divided by answer. I get 8.9 newtons. So then if I go back to this right here, hopefully that makes sense. But I go back to here, I'm going to get 8.9 newtons minus mu s times 49 equals 0. So then if I say 8.9 divided by 49, I get mu s to be 0.18. 0.18. So that would be that. But here's the thing, okay, just so you know, this is not a very big mu, but that's okay. That's the minimum mu just for my ladder. Chances are that the actual mu between your ladder and the ground is going to be much bigger than this, because guess what? If you walk up this ladder, if you climb up there, now there's going to be a force of you going down, and so then it needs to have more friction so it doesn't slip. But anyway, basic steps. Hopefully that makes sense. Bye, kids.